Okay, good afternoon. Let's get started. For today's lecture, we'll talk about self-supervised learning. So before we go to self-supervised learning, so first let's look at the main learning paradigm in the conventional machine learning. So we have the supervised learning and the unsupervised learning. So for supervised learning, we've talked about a lot from the first couple of lectures. When we're starting to talk about the deep neural network, right? So we use image classification as the task, and we do the supervised learning. So basically, the supervised learning setting, in order to train the algorithm, not just deep learning, any machine learning algorithm, we need to have some training data, right? So that's the training sample as well as the corresponding label, right? So the ground truth label will serve as the supervision signal or information to guide the optimization of the network, so that the network or the machine learning algorithm learn is able to predict accurately on the test data. So if you look at the figure on the left, this green box showing this is supervised learning, right? So this is a very simple example of binary classification. We have two classes, one indicated by this blue circle, and the other classes is indicated by this red cross. So this circle and the cross indicating the label information, right? So we can using this label information to train this classification network in a supervised manner, okay? So for the unsupervised learning setting, that means we don't have any label information, right? So if you look at here, so all the label information has been removed, right? Basically, we have these 8 data points, right? But we don't know any of the label information. So but we still want to, discover some of the patterns from the data, right? So we in this case, this is unsupervised learning. We can using some, for example, clustering algorithm to find some of the intrinsic patterns or characteristics of the data. Maybe this set of data has similar features, so they close to each other in this feature space. And this is another set of a set of data, right? They form another cluster based on the features, right? So we can do this kind of clustering to do this kind of data discovery or pattern discovery in an unsupervised manner, okay? So in between these supervised, unsupervised, there's also some other settings. One is called the semi-supervised learning. So in this semi-supervised learning, we have a small amount of labeled data. In addition to that, we also have a large amount of unlabeled data, okay? So in the semi-supervised, right, you have a small labeled data set, and you also have a large number of unlabeled data. So this is often the case in real-world application. For example, in a lot of industry applications, right? So maybe due to the time and the label cost of annotating the data, right? So maybe those kind of applications do not have a lot of labeling budget, right? But in order to train the model to the expected accuracy, we need to spend some of the cost or time to label a small amount of data, right? So you end up with a small set of labeled data set, but you do have a lot of unlabeled data. So in this case, we don't want to only relying on a small set of the labeled data to train the model, but we also want to leverage the knowledge that resides in a large amount of unlabeled data, right? So this is the semi-supervised learning. And in between, we also have a setting called weakly supervised learning. So this is, again, serve the same purpose, right? So we don't have a lot of budget to label a lot of data. In this case, we can we can provide some cheap labels, right? Just give you an example here. Here, the task is doing image segmentation, right? So we have to label each of each image, right? So in order to, if you do this kind of pixel-wise labeling, that's going to be very time consuming, right? But we can do some cheap labeling, right? Instead of doing every pixel here, they are doing this kind of scribble, right? So basically you just draw a line based on the image, right? So this is very easy to do, right? So a human annotator to look at the image, then quickly draw a line, right? So this line has, contains some of the pixels corresponding to one particular class, right? So in this example, this line corresponding to the semantic class of sky, and this line, green one, corresponding to another semantic class of tree, right? Cow and grass, right? So compared to do this kind of very accurate pixel-wise labeling, this kind of scribble, this labeling is going to be much quicker, right? So you just draw a couple of lines, then you can move on to the next image. But if you will sit there and do this kind of pixel-wise labeling, it's going to be very time consuming. So basically you have to draw this very complex contour to separate these different classes to make this very accurate annotation. And the reason it's called weakly supervised, right? Because this supervision is considered a weaker supervision as compared to this the ground truth mask or segmentation annotation, right? Because there's still a lot of pixels in this original image don't have any label information. You only have a small set of pixels has the label information. So this is considered a weaker supervision. Okay, so the scribble is one form of weaker supervision. In terms of the task of semantic segmentation, there's also other weak supervision you can think about is instead of draw a line, right? Maybe we can also draw a bounding box, right? Or maybe draw a circle, right? So these are all weak supervisions we can provide. So this will, largely improve the annotation efficiency. Okay, and there's also other weak labels for different tasks. For example, we can have video level label, then we can using this video level label to infer image level label, right? So maybe in this video, there's different objects in the image, but if you provide a general weak supervision in the video level, then we can using that knowledge somehow to classify the object in different images. So that's another form of weak supervision for a different application. And self-supervised learning is a subset of unsupervised learning methods. So it refers to learning methods in which algorithms are explicitly trained with automatically generated labels. Okay, so here we want to kind of define or differentiate two types of labels. One is the human annotated label, right? So this is mostly corresponding to the supervised learning task, right? When we talk about the ground truth label, we all refer to this human annotated label, right? Because we consider the human as an expert and the label information will be correct, right? So we use that as a ground truth. And another definition here is the pseudo label, right? The pseudo label are automatically generated labels based on the data attributes for some of the pretext tasks. So I can give you one form of as an example, right? So the pseudo label can be, for example, if you rotate image into a certain degree, like 90 degree, 180 degree, right? So the rotation, the rotated angle can be a form of a label, right? How much, what are the angle this image has been rotated, right? So this kind of labels can be automatically generated, right? Don't require like a human effort, right? So you can essentially write a couple of lines of code, right? Or write a program to automatically to rotate image to a designated angle. Then you can using that as the label information for this pretext task. Okay. Of course, there's many pretext task we can think about, right? So this kind of rotation is one simple and easy task we can achieve and generating the corresponding label information. And we will talk about different pretext tasks for self-supervised learning later. But first, we want to understand, right? So how this self-supervised learning is able to help to learn a meaningful representation, then we can using this representation for some of the downstream tasks. Okay. So the idea of this pretext task is we can design some of the task for the network to solve, right? The rotation is one task we can design for the network to solve, right? To predict the rotation angle. And in this case, the visual features can be learned through this kind of pretext task objective, right? Predict the rotation. So if we have this unlabeled data set, right? So we feed this unlabeled data. So here we are talking about images, and we feed these images into this, classic CNN network. We generate some, extract some features, and we do this prediction. For example, the rotated angle, right? So we have the pseudo labels. We can define an objective function, right? We can compute the loss and optimize the network. So this CNN network, so that this network is able to learn some meaningful representation from the data. Once we train this network in this pre-test task, right? Still, we consider the rotation as an example. Then we can take the knowledge learned through this pretext task and for the downstream task transfer, right? So in this case, we may have only have a small set of labeled data, right? So maybe here we're only interested in classifying, let's say we only interested in classifying different types of birds, right? So then we can using the pre-trained model and fine-tune it, right, on this small set of labeled data set and perform the downstream task, which is bird classification. So that's the general idea or framework of self-supervised learning, right? So define some pretext tasks by define some of the but learn the representation by defining some pretext task and using that learned representation and fine-tune it for the downstream task. So why do we care about self-supervised learning, right? So why do we want to spend or devote the effort into self-supervised learning? So the reason is very simple, right? Creating label data set is very expensive and time-consuming, and it requires human labelers, right? Preparing the label manual, creating some of the GUIs, and also creating storage pipeline. So there's going to be a lot of time and and money invested for this kind of human labeling. And high quality annotation in certain domains can be particularly expensive, right? Especially in the medical image computing domain, right? So we want to annotate like tumors, different organs, right? So we need to ask. Actually, the human labeler may need to have a medical or healthcare related degree, right? Otherwise, this kind of labeling, the quality of the annotation may not be high enough, right? We cannot ask a random people, right, to annotate some of the medical data if they don't have the expert knowledge in this domain, right? So in this case, this higher quality annotation can be very expensive, okay? And the self-supervised learning can take advantage of the vast amount of unlabeled data on the internet, right? So because the pseudo labels we generate in the self-supervised learning can be automatic, right? So we then can collect a lot of unlabeled data, right, from internet, for example, images and videos, right? So especially here we have a lot of social media platform that essentially give us the opportunity to collect infinite amount of data, right? So these kind of rich discriminant features can be obtained by training models without actual label and through this big data. And self-supervised learning can potentially generalize better because we learn more about the world, right? Because we are collecting a lot of unlabeled data on the internet, right? So you can have much more diversity as compared to you collect a set of labeled data, right? So the set of labeled data may not be represent the data distribution in the real world, right? But if the data is large enough, then the distribution can become more similar. Okay. But there's also several challenges for self-supervised learning. One is how can we select a suitable pretext task for application, right? How do we basically come up with the idea or come up with the self-supervised signal, right? To learn a meaningful representation. And the second is there is no gold standard for comparison of learned feature representations. For some of the applications, maybe one particular self-supervised learning is able to perform better, but for some applications, maybe the representation is not able to generalize well. So there is no gold standard for the comparison of the learned feature representation. But in the literature, we do have some of the experiment or settings to evaluate the performance, which we'll talk about later. For example, this kind of linear evaluation, fine-tuned evaluation. Okay, so here I summarized the general step for self-supervised learning. So the step one is we learn the visual feature is learned through the process of training the neural networks to solve a predefined task, right? Image rotation prediction. Then the learned parameter will serve as the pre-trained model and transfer to the downstream task by fine-tuning. Okay, so that's the general process for self-supervised learning. And here, this is kind of give you a graphic illustration, right? How this self-supervised pretext training is performed, right? So you have an unlabeled data set, then based on the pretext task, you will generate the pseudo label, right? P1 to Pn, okay? And with this pseudo label, then you can train the network and just do this as like a normal supervised training, right? You generate this output, and you can using this based on this output and compare with this pseudo label P1 to Pn and compute the loss, right? If this is a classification task, then you can have this cross entropy loss, and you can using this loss to guide the training or optimization of the network. In this survey paper, they provide several categories of pretext task. So they can basically divide into these 4 different categories. So one is the generation-based methods, right? So this pretext is is defined as generation. Here, the generation can be, if we're talking about image, right? It can be image generation using GAN. Super resolution is also a type of image generation. Basically, you want to generate a high resolution image based on a low resolution input. Image encoding is you want to basically fill some of the missing parts or regions in an image, right? So that's image encoding. And image colorization. So maybe you have a grayscale image, then you want to generate the corresponding color version, right? And for the video case, we can apply a similar technique, right? Using video generation, using GAN, video colorization. And also, because video is a spatial temporal data, right? So we can using future frame prediction, right? Based on the current observation of the video and predict maybe the future, maybe 10 or 30 frames, okay? So these categorized as generation-based method to learn some, based on this kind of generation task, hopefully the network is able to learn meaningful representation. And we'll also have the second category is the context-based methods. And so the idea is we can, based on some of the spatial context of the data, right, in particular images. So there's a couple of popular pre-text tasks. For example, this image jigsaw puzzle, right? So we can divide the images into small pieces or patches, and to make like a puzzle, right? We can shuffle these patches and then make reorder them into the right order, and trying to get back to the original image, right? So this requires the network to understand the context, right? Otherwise, you cannot recover the original image, right? If you don't understand the context of the image, you are not able to. The network is not able to predict the correct order of these different patches. And geometric transformation, and there's also context similarity, right? So we can do clustering, and based on clustering to generate some pseudo labels to guide the training, right? Using the pseudo label to do the supervised training. And for video case, we can of course do this kind of jigsaw puzzle, right, in the spatial dimension, but we can also do this kind of frame order verification, right? We can shuffle the frames in the original video. Then we ask the network to predict what is the correct order of these shuffled frame, right? Another category is the free semantic label based method. So in this case, we can using some of the hard code algorithm to generate semantic labels, right? So maybe we can use using like the motion information, right? We can compute the motion vector. If you process a video, right, we can compute the motion vector between consecutive frames, and using that motion to kind of highlight or get a rough annotation of the moving object, right? Then we can using that label information to train a network to segment the moving object. Okay, and in this category, there's a lot of work trying to use game engines to generate this freely, semantic labels, right? In a lot of these game engines, like Grand Theft Auto, right, GTA, we can using these game engines to create things by place, different object or things, right? Essentially, we create these semantic labels, then the game engine will rendering the corresponding, things, right? Then we can using that as the training data to train a network. And the last category is the cross-model based method. So basically, the data will have multi-modalities, right? So, for a lot of video footages, we not only have visual appearance, right? We also have the corresponding audio information, right? So, for example, there's maybe a player is playing a guitar in this video, right? We have the visual appearance of the player playing the guitar, but we also have the corresponding audio information, right? Then we have this one-to-one correspondence, right? So in this kind of time interval, this player is playing the guitar, and that's the corresponding audio information. Then we can build this kind of relationship and use that to train a network to predict this kind of correspondence. So some of the details we'll introduce when we talk about this individual approach. Okay, so yeah, let's look at this particular example, solving the jigsaw puzzle, which is very popular. And so the idea is that, right, so you have an image. So in their method, they do not consider the entire image. They maybe select a portion, right? So this crop of image, and they divide this region into 9 patches. Okay, so 3 row and 3 column, right? You have 9 patches, and you take the center patch, right? This blue box as your query. Okay, so given this center patch, then and also you randomly pick one. Okay, so in this case, this selection picked the patch numbered 3, and the pre-test task is trying to predict, right? What's the position, given the center patch and the selector one, what's the position of, in relation to the center one? Okay, so basically you want to predict 8 number, right? 1, 2, 3, 4, 5, 6, 7, 8, right? Because we have these 8 patches you can select, and these are the original position, right, from the original image. Okay, so in this case, you can easily think, right, the pre-test task is going to be a classification problem, right? It's a 8-way classification, right? You have 8 classes, right? Because you have 8 different positions, in relation corresponding to the center patch. Okay. Yeah. So for this example, right? So the ground truth should be 3, right? Because this is how we divide this, patch into these 9 patches, and this is the ground truth position information, right? If you select another patch, which is here, then the ground truth will be 5, right? Another one here, this ground truth is 1. Okay, so so this label can be easily generated, right? Do not require like much human effort, right? You can write a program, divide the image into 9 patches, and you can automatically generate the label for this individual patches. Okay. So if you look at it, right, so you have this in their network, they have like a 2 stream of network, right? Because we're gonna process these 2 patches, right? So the center is gonna be always there, right? So you have patch 1, that's the center patch. You go through this CNN network, right? AlexNet, a couple of COM layers, pooling layers, FC layers, and you extract the feature, right? So another one, which is randomly select a patch, you go through the same network, extract the features, then the output will be predict the position, right? The position, right? So this is the 8-way classification problem, and since when we generate this kind of pre-task examples, we know the ground truth label, right? So we can using this to guide the network optimization, compute the loss and optimize the network. Yeah, so in this case, we can treat it as the normal supervised network training. Okay. So this is another example, right? So this is a different image, and you basically do the similar process, right? Divide the crop or region into these 9 patches and take the center and trying to predict, right? If you random select a patch, what's the position in relation to the center one. So this is based on the context, right? You want to do this kind of context prediction. Okay. And this figure shows that, trying to evaluate, right, if the learned representation is meaningful. Okay. So on the left side is the query image. Let's see. And this one, sure. Okay, so the first column here is the feature of the random initialized feature. Okay, so we want to, extract the features like FC6 layer features, right? We want to do clustering, right? So basically based on this query image, and we retrieve based on FC6 layer to retrieve the corresponding images. As you can see here, if we randomly initialize this AlexNet, right? We're using the random initialized feature representation. The retrieved image is basically random, right? So here you have a query, which is the tire of the bike, right? But you retrieve all kinds of different images, right? River, these plants, bridge, whatever, right? Here, the second column, right? This portion here is the supervised trained Alex network, right? Using ImageNet during the supervised training, which means you have using the ground truth ImageNet label to train the network, and using that feature to do the retrieval. As you can see that these features are very good, right? You are able to retrieve images corresponding to the same class, right? This is maybe the leg of the horse, right? The cat, the airplane, right? So the retrieved image all belong to the same class, okay? The last one is the the FC6 feature learned from the self-supervised learning method, right? Doing this kind of context prediction, right? If you look at these retrieved example, right, they all belong to the same class as the query, right? Which indicating the learn feature through this self-supervised learning task is also meaningful, right? It's kind of learn similar things as compared to this kind of supervised training, okay? So these, the upper portion is the successful case. They also show some of the failure case, right? So in the bottom portion, so this is the keyboard, right? So this image here, the supervised training has no problem, right, to retrieve the right image, right, corresponding to the computer keyboard. But in the self-supervised learning, right, so they are some of the images are not correctly, so which means the learned representation is not as good as the supervised training, which is understandable, right? Because we don't have any label information. We are just using some pretext task to train the network. But from some of the successful case, still the learned representation are meaningful, okay? And the follow-up work also using this jigsaw puzzle, but just make the task more a little bit more complex, okay? Instead of taking the center patch and randomly select one to predict the position, here basically you use all the 9 patches and you shuffle all these patches to a puzzle, right? And basically you just want to recover to do this kind of the ordering information of these patches, right? Just like a human, we do this kind of puzzle, okay? So the task will be, if you have 9 patches, right, you have a large number of permutation, right? So you can shuffle all these patches and get different permutations. So to make this method easier to solve, right? If you just shuffle all these, then you have like 362,000 or more possible puzzles, right? This may be make the task too complex. So what they do is they predefine 64 shuffling permutations, right? You just define just 64 permutations and do this for all the images in your unlabeled images in your set, and do this randomly and ask the network to predict, right, which permutation this input belongs to, okay? So again, this is a classification problem, right? Doing this 64 classes classification. And this is their network, right? So you have, these 9 patches, right? The shuffled patches, and they go through this, the same network, right? One thing to note is that although you can see there's like 9 different networks, essentially this is the same network, okay? So the same network architecture sharing the same weight, but it's just when they illustrate their method, they do this like in parallel, okay? But in the implementation, this is the same network sharing the same parameter weights, and basically go through this network, extract the features, and trying to predict the permutation, right? One out of this 64 permutations, okay? So once the network is trained using this self-supervised learning task, right? They using this pre-trained weights, and freeze them, and you can take this pre-trained network and fine-tune it on the downstream task. So if you don't want to do the full fine-tuning, right? So you can freeze these pre-trained maybe conv layers and only fine-tune the classification layer, right? Maybe your task don't have like a 64, right? If you're doing this task, right, you have 64 classes, but in your downstream task, maybe you only have 10 classes. For example, you're doing CFAR10 classification, right? You definitely have to retrain the classifier layer in order to perform the downstream classification. But you can freeze the conv layer, right? Which, through the self-supervised learning, you already learned some meaningful representation. And this is the result they performed for this Pascal VOC detection and classification. And the first row here is the AlexNet supervised training on the ImageNet, right? So they list a couple of metric here, right? How long to train the model in the supervised manner, right? So they have 1,000 classes labels, and they train 3 days and do this classification on the VOC. Okay. And this number 10 is the spatial context prediction, right? So to using the center patch and predict the position of a randomly selected. And it took 4 weeks to do the pre-training. And they don't using the ground truth label to do the supervision, right? Just using the context. So this is a self-supervised learning approach. And this is the classification result on this VOC data set. And this is their proposed method, which is using this puzzle, okay, predict the permutation. And so based on the result, right, it's not far behind the supervised approach, right? If you just look at the classification, like 10% gap as compared to the fully supervised training, right? Which is not bad, right? Because we are not using any of the label information during the pre-training, okay. The second approach is the using context is the colorization, right? So basically, you have an input, which is grayscale, don't have any color information. The output will be a color image, right? So the reason this method works is because, we need to understand what the object is, right? Before predict the color, right? If you are not able to understand this is the flower or this is a butterfly in this particular example, then maybe the color predicted may not be accurate, right? So this is another example, and also like apple is red, right? Sky is blue, right? So these all require the network to understand some of the semantic information of different objects. So that's why the trained network is able to learn some meaningful representation that is helpful for the downstream task transfer. Okay. This is like an improved version. Rather just input a grayscale, go through this network and predict the color. So here they do this kind of like a split brain. They call it split brain autoencoder. So basically you have the input image, which is color, right? Then you can decouple the texture and the color information, right? So you separate this image into a grayscale and also the only the color component, right? And on this one stream, you have this grayscale image and you have a predictor F1 to predict the corresponding color channels, okay? And on the other stream, right, you have the color channels and you have another predictor to predict the corresponding grayscale channels. Then you can using the predicted color and those grayscale channels to form the predict image, okay? So this is how they learn through this kind of colorization process. The next pre-test task is image inpainting, right? So what you can do is take this unlabeled image, right? Maybe crop a small region in the image and go through this seeing network called encoder to encode the features. And then you go through another decoder, right? Trying to reconstruct the missing piece, right? Which is the center crop out region, right? And of course you have the ground truth, right? Because from the original image, you crop out this region, right? So you know what exactly, what is the ground truth content for this image, right? So you can compare the reconstruct patch with the ground truth, right? Using some, like in the L2 sense, right? L2 dimension, right? So you can using the L1 or L2 loss, or maybe using some other visual quality assessment like MSE or SSIM, okay? In addition to this reconstruction loss, they also put a adversarial loss, right? So basically you can also, append a discriminator, right? To kind of judge, right? If the reconstruct or predict the patch is going to be realistic or not, right? So basically they want to adding this adversarial loss, trying to enforce the decoder to predict a realistic patch. So that's their overall loss to train the decoder. Okay, so once the network learned, then you can using this representation from this encoder and decoder structure. Okay. And this is some qualitative result from their paper, right? So you have this input and you crop out this centerpiece, and this is the in-painted image, right? Basically reconstruct the missing piece. And as you can see that the reconstruct image looks decent, right? So they're able to reconstruct some of the missing piece, but it's not perfect, right? For some of the images, right? This crab image, maybe the shape is not as close to the original image, but some of the information like the colors, the contours are very similar. Okay. And this is their result, right? So they also using their trained network, right, in the self-supervised learning, and fine-tune it for the classification and also for the detection and segmentation task. And they compare with the supervised manner, right? This is the ImageNet supervised training, right, using 1,000 class labels. And this is you can consider this is the upper bound, right? Because we want to get as close as possible to the supervised training approach. Okay. So the next approach is doing the rotation, right? So in this example, right, as I mentioned, you can rotate this image in to different degrees, right? So in this case, the network trying to recognize the rotation and predict a rotation angle. Okay. So this again, just like the permutation, right, jigsaw puzzle, right? This is again a classification problem. You have a image, and then the pseudo label will be rotation angle, right? So you input this image and extract the features and ask the network to predict the rotation angle. So you can train this in a supervised manner, and hopefully the network is able to learn meaningful representation. And the clustering is another method. So in this paper, they have the unlabeled input, right? Go through this CNN network and generate some feature representation, right? A feature embedding. And based on the feature embedding, you can do unsupervised clustering, right? You can using some clustering algorithm like k nearest neighbor to form k clusters, right? And then each of the cluster can be considered a pseudo label, right? You don't have to specify what class that is. It's not necessary, but since you have k classes, right, then you can designate a label for each of these data points, right? For this particular cluster, then you can label as class 1, this one class 2, right? This is the pseudo label generated by clustering. Then you can using the pseudo label to guide this to train the network in a supervised way, right? And you can do this iteratively, right? In the very beginning, the pseudo label may not be very correct, right? So, but after a couple of iterations, because you're using the pseudo label to optimize the network, and the network may learn some meaningful representation over the time, so that the clustering can be more accurate. This will improve the pseudo label accuracy, right? Reduce the label noise, and you do this iteratively, and hopefully, at the end, the representation learned can be improved as well. So here are some of the result, a comparison of different approach, right? This split brain is the colorization and jigsaw puzzle, and this deep clustering, which we talk about in the previous slides, and also predict the rotation, right? So here, this deep clustering performs pretty well, right? So as compared to other different pre-test tasks, right? Deep clustering is able to achieve 73.7 classification accuracy, right? If you compare with the supervised training, right? The ImageNet label, right? So we consider this is the upper bound, right? So here we only have about 6% gap, right? So it's kind of getting close to the upper bound, okay? And the rotation prediction also perform very well, right? As compared to other like a jigsaw puzzle or colorization, right? So the classification accuracy is very close as compared to this deep clustering. So I think the rotation is a very simple pre-text task, but at the same time, it is able to perform pretty well. So maybe in your own application, based on this kind of result they presented in the comparison, the rotation can be maybe a popular choice, right, to design the pre-text task, or at least a top choice you can try, right, before you maybe try other pre-text task. Okay.